The things I enjoy doing aren't limited by the game development and software engineering. I also love explaining nerdy topics in nerdy way. So I decided to create this educational video to explain floating point numbers and hopefully grow an audience a bit. The script was corrected with the help of ChatGPT and narrated by me to add some personality, despite my far not a perfect accent. Right now in the video you can see how the 3D model of the car gradually starts looking more and more unstable. And this happens as an error of the floating point increases as the value gets larger. In this case, this value is the distance from the world origin. I hope you find this video interesting. In the games like Roblox, Minecraft, and some other games with large-scale environments, you have probably noticed strange visual glitches when the characters move far away from the world origin. Things start shaking, jittering, wobbling, you name it. These aren't graphical bugs. They are the result of the floating point precision errors. Here you can see the car from Suku Race with the exaggerated floating point error in action. It was achieved resetting the least 20 bits of Mantissa to 0. Explained later. All data in a computer is represented in bits. A bit is an abstraction that can store either 0 or 1 with no intermediate values between them. Real numbers, which can be fractional like 1.45 or minus 7.61, are stored in a computer as 32 or 64-bit floating point numbers. The number of bits is typically limited to 32 or 64 bits respectively. What is floating point and where does it float? Fractional numbers have a decimal point. Let's look at the number 3.141. What happens if we move the point? 3.141, 31.41, 314.1. We can represent these values as 3.141 times 10 to the power of 0, to the power of 1, to the power of 2. In each case, we move the point to the right, making the number 10 times larger with each shift. This is why the point is said to float. As mentioned earlier, floating point numbers have limited number of bits. Let's imagine we have 4 digits for the number and 1 digit for the exponent. By increasing the exponent, we shift the point to the right, and the largest possible exponent is 9. So the 3.141 with the largest exponent becomes 3,141 millions. As you can see, the least significant digit is in the millions. The smallest meaningful digit in a number with exponent 9 with our limitations is 1 million. You can't represent anything smaller than that with exponent 9. And if you decrease the exponent, the entire number changes dramatically and may no longer represent what you intended. In this case, when you want to add 3.141 times 10 to the power of 9 plus 25, that equals 3,141,000,025. But we have a space for only 4 meaningful digits. So this number remains 3,141,000,000 because it is stored as 3.141 times 10 to the power of 9, and there is no space to store 25. Let's go back to our floating point numbers and their bit representation. The most common floating point standard is IEEE 754. The most common means it is supported by almost every server, desktop, or mobile device. Floating point number operations are implemented as a specific set of transistors etched into the arithmetic logic unit ALU of modern CPUs and GPUs. CPUs have full hardware acceleration of both single 32-bit and double precision 64-bit floating point numbers. Most consumers' GPUs, however, offer high performance for single precision floats, but have very limited or sometimes no support for double precision. As a result, when discussing graphics or general-purpose GPU computing, we usually referring to a single precision floating point numbers. Here we will discuss a single precision 32-bit floating point format. A 64-bit float is much more precise, but there is no point discussing it here. The idea is the same, just with more bits. The 32 floating point has 1 sign bit, 8 exponent bits, and 23 Mantissa bits. This value is actually near 0.1. Why near? I'll explain later. The sign bit is the most straightforward. 0 is positive number, 1 is negative number. So switching this bit to 1 make the number negative. Exponent is basically an 8-bit integer number. The value of each bit increases 2 times each step to the left. Least significant bit value of the exponent is 1, and bit itself is set to 1, so we take it into account. The next to the left bit value is 2, and the bit itself is set to 1, so we take it into account as well. The next bit value is 4, but the bit itself is set to 0, so we skip it. The most significant bit value is 128. So the current exponent value is 0 times 128 plus 1 times 64 plus 1 times 32 plus 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1 equals 123. Let's remember this number and talk about Mantissa. Mantissa is the fractional part of the floating point. The value of the first Mantissa bit is 1/2. The value of the next to the right is 1/4. The bit value decreases 2 times each step to the right. So the actual Mantissa value is 1 divided by 2, 0 divided by 4, 0 divided by 8, 1 divided by 16, and so on, 0 divided by 8,388,608. The sum of this series is near 0.6. And what does it mean? The actual value of floating point is minus 1 to the power of sign, it means 1 minus 0 plus, times 2 to the power of exponent minus 127, times 1 plus Mantissa. As we found earlier, the value of our exponent is 123 and Mantissa is 0.6. By substituting the values into formula, we get near 0.1. Why near? Floating point can store the exact value of 0.1. As we mentioned earlier, bit can store either 0 or 1, and changing the least significant bit makes the number a bit bigger or a bit smaller than 0.1, but never exact 0.1. You can find plenty of memes about this on the internet. Let's talk about the properties of the floating point. Let's get a positive floating point number with exponent bit value 0 and 7 ones. That is 127. The exponent scale will be 2 to the power of 127 minus 127, and that will be 2 to the power of 0, that is 1. Let's set all Mantissa bits to 0, and now let's try to calculate the result. We already know the formula for calculating Mantissa. As all bits are set to 0, the sum of this series is 0. So substituting to this formula, the result will be 1 times 2 to the power 127 minus 127 times 1 plus 0. That will be 1 times 1 times 1, that equals 1. Let's set all Mantissa bits to 1. That will be 0, 0 and 7 ones of exponent, and 23 ones of Mantissa. Substituting all these bits to the Mantissa formula, we get geometric series 1 divided by 2, 1 divided by 4, 1 divided by 8, 1 divided by 16, and so on. For an infinite geometric series, the result will be 1. But we have only 23 terms, and the value of the least significant bit is 1/8 millionth. So the sum of this series will be almost 1. 1 minus 1/8 millionth. So substituting these values to the floating point formula, we get 2 times 0 times 1 plus just under 1, and that will be just under 2. So with exponent 127 that represents a scale 1, we have a range of values between 1 and 1.999999, almost 2. And with this exponent, we cannot store a value 2. To store 2, we should change exponent to 128 and reset all Mantissa bits back to zeros. So 2 to the power 128 minus 127 times 1 plus 0 equals 2 to the power of 1 times 1 equals 2. With exponent 128, we get a range from 2 to almost 4. Increasing the exponent again to 129, we get a range from 4 to almost 8. With exponent 130, 8 to almost 16. We can go an opposite way by decreasing an exponent to 126. 2 times 126 minus 127 equals 2 to the power of minus 1 equals 1 half. The range of floating point with this exponent will be from 0.5 to almost 1. By decreasing the exponent again, we get a range from 0.25 to almost 0.5. Let's go back to exponent scale 1 and determine the accuracy of values in range 1 to almost 2. The value of the least significant bit of Mantissa is 1/8 millionths. That's a precision of the floating point in range 1 to almost 2. That is 1.2 times 10 to the power of minus 7. But each time we increase the exponent, the error increases by the same scale. Let's discuss errors in the context of the metric unit system. So in the range from 1 to almost 2 meters, we get a precision 1/8 millionth meters. That is 120 nanometers. Let's go back to the car. Placing the car to the world origin, it's impossible to notice 120 nanometers error. But what happens if we move the car 100 kilometers along the axis X from the world origin? We start seeing noticeable wobbling in the car. 100 kilometers is 100,000 meters. The exponent is 143. That represents a scale of 2 to the power of 16. That is 65,536. Let's calculate the value of the least significant bit of Mantissa. That equals 2 to the power of 16 divided by 2 to the power of 23. That equals 2 to the power of minus 7. That is 1 divided by 128 equals 8 millimeters. We can place a car by 1 million meters away by axis X, and we see the car feels quite bad. At 10 millions, you cannot recognize it at all. By the way, double precision has 52 Mantissa bits. That's 29 more than single precision. This makes double precision about 2 to the power 29, or roughly half a billion times more precise. At distances like 20 million meters from the world origin, where single precision completely breaks down visually, double precision still operates at nanometer level accuracy that's completely unnoticeable. But since most consumers' GPUs either don't support double precision or support it with very poor performance, we typically don't use it in real-time 3D graphics applications. Back to single precision. Let's see the error impact if we place an object at 2000 kilometers from the world origin along forward direction axis X. Object right direction axis Y. Object's up direction axis Z. You can see an interesting effect when looking from Z-axis. You see almost no error. The error is in the depths, so you might notice that fighting in some areas, like wheels are visible through the car body. Here you can see an error at large distances along X, Y, and Z. Let's place a car at a distance of 2 to the power 23 by axis X. That's 8 million meters. As we already know, the error in 32-bit IEEE 754 floating point is 1/8 millionth. An error of 1/8 millionth at a distance of 8 million meters is exactly 1 meter. That's why on the left side you can see the 1 meter discreteness steps. At the front of the car is 2 to the power 23 exponent scale zone. On the right side, the rear part of the car is in exponent scale zone 2 to the power 22, 4 million. And since the error increases and decreases with the exponent, you can observe the half meter steps in position. For the same reason, after 2 to the power 23, 8 million, there are no fractional values in floating point anymore. The least significant bit error is 1. This means you can't represent a number like 8,388,608.5 or 10 million.5. At the exponent scale 2 to the power 24, 16 million, the floating point starts skipping integers because the least significant bit value becomes 2 and only even numbers can be represented. The error occurs not only at large distances. Even at smaller distances, there can be a slight effect. Let's look at an object placed 1,500 meters away. This could be the distance from their world origin in the game level, where a small wobbling effect starts to appear. It becomes noticeable in fine details and during smooth movements. There is a low chance to notice it in fast action games. Let's move from graphics calculation to another type of floating point computations. The problem can arise when incrementing a large values. The simplest example is calculating the time from the beginning of the game, like time equals time plus delta time. If our game or simulation runs at a refresh rate of 60 frames per second, it will accumulate a time delta of 1/60th each frame, that is 0.016. By accumulating 0.016 60 times per second, we increment a value in 1 per second. However, if the floating point error of the time variable exceeds 0.016, the time variable will no longer increase. The time completely stops after almost 5 days of playing. Let's be real, nobody's going to play that long anyway. Maybe. By the way, playing for 32 hours, the increment value becomes 0.0156. After playing 72 hours, the increment value becomes 0.03, so it increments almost twice as fast. So instead of playing 524,000 seconds or 145 hours, the time stops after 115 hours. But if you have a refresh rate of 144 frames per second, the time stops after 32 hours of playing. So if you are going to accumulate large values, use double precision floats. Using 64-bit floats, you can play a game for several million years. That's much better. For the same reason, you may have difficulty trying to move an object at slow speed far from the world origin. The position increments each frame in the next way. New position equals old position plus velocity times time delta. You can face the same problem when the value starts incrementing faster due to floating point rounding, and then the movement stops. When you try to move at an angle relative to the axis, you may notice that the object might move slow along the axis instead of the intended direction. By the way, this camera has a double precision float position. But if I change the precision to float, I can pan view slowly. Only abrupt mouse movements move the camera. Most modern game engines use double precision floating point numbers for object transforms. They also implement various workarounds to maintain visual precision in open-world games or large environments using 32-bit floats. The main idea is to keep camera and close to the camera objects near the world origin, even if you are far from the actual origin of the game world. This can be achieved by shifting the entire world when the player moves beyond a certain bounds. Once player steps outside the square, the whole world, including the camera and all seen objects, is shifted back to keep the player within the high precision zone. The Unreal Engine has a similar approach named Large World Coordinates. And one more important thing. It doesn't matter which unit system you choose. Metric, centimeters, like in Unreal or Unity, inches, miles, whatever. An object 10,000 centimeters away from their world origin will have a much larger error per unit than an object 100 kilometers away. But since both the object and the camera distance are 100 times larger, the visual impact of the error remains the same. And as final note, with an exponent value of 254 and all ones in Mantissa, the maximum finite value in single precision floating point is approximately 3.4 times 10 to the power 38. An exponent of 255, all ones in exponent field represent either infinite or none. None is not a number. Infinity has all zeros in the mantissa. It can result from operations like overflowing the maximum representable number or dividing any non-zero rational number by zero. None, not a number, represents invalid results like infinity minus infinity, infinity divided by infinity, or zero divided by zero. Nonce have at least one non-zero bit in Mantissa. An exponent value of 1 with all zeros in Mantissa gives the smallest normalized number, which is 2 to the power of minus 126. An exponent of 0 indicates a subnormal or denormalized number. This represents values smaller than 2 to the power minus 126. And unlike normalized numbers, they don't have an implicit leading 1 in the Mantissa. Subnormal values are often disabled by hardware to improve performance. That's all I wanted to say for today. Thank you for watching. Bye.